Okay, so here we are with table L. It's an AP table, or at least it's a table that's beyond the scope of the New York State Regents. But really what it is, it's a Ka table. And as the table suggests, it gives us the relative strengths of the acid. Now, a strength of an acid is built in the idea of how well an acid will completely dissociate. Now, what I mean by that is, if I have an acid that completely dissociates, that means let's make this HA. Okay, and let's say we have a bunch of HA molecules. Now, if it's an HA molecule, that means that it will dissociate completely if it's a strong acid. Dissociation means breaking apart. So all these HA molecules will become A negatives, and that A negative represents the conjugate base. If you notice on table I have here, here are your acids, and your bases, what we call conjugate bases. Most of these guys are negative. They lose their proton, and now they have more electrons than protons overall. It's a negative charge. Now, not all are, but most are negatively charged. So here's our conjugate acid, and here's our conjugate bases. Now, our bases, or conjugate, as it says in the table here, mean nothing, that only just mean that it's the same chemical plus or minus an H. Okay, so the acid has the proton, the base lost it. Okay, in any case, what we have here is that all of these HAs become dissociated. That's what we call a strong acid. Strong acids completely dissociate. Now, why? Well, in part, it's because of the inability of the conjugate base to actually accept the H pluses and reform the acid. So the reverse just does not happen. Okay? So these are really one direction, very spontaneous, okay, reactions. Okay? So these strong acids have a lot of ions, and they're very good electrolytes because they produce a lot of ions. Now, if you remember, KEQ is nothing more than the products of the reactants. Coefficients become exponents. Solids and liquids do not apply. So it's a ratio of products to reactants, so to speak. Okay, and if KEQ, if you remember, is larger than 1, okay, that means that there is a lot more products favored when this reaches equilibrium. Now, if a lot of products are favored, you'd have a high KEQ. Since all of these are acids, and we're going to use the value of KEQ to measure how many ions, because the ions are products, more products, higher KEQ, we're going to change this KEQ to call Ka. It's an acid dissociation constant, keeping temperature constant because remember that temperature affects equilibrium. We know that, well, the Ka or the KQ, it's the same thing, kind of like KSP for salts. We call it Ka because these types of reactions are acids breaking apart. And if the Kas are large or very big, that means we have a lot of products, which means we have a lot of ions, which means the acids dissociate very well and are stronger. Now, strong acids, if you notice in this table, okay, at least the ones listed, and they have 5 listed, and we're probably missing 2 more from this table. It's not comprehensive. Perchloric acid, so HClO4, and chloric acid, HClO3, are strong acids that would be in this list in the mix somewhere. But they left those out. In any case, their Kas, if you notice, there's no number associated with them because, well, they have such high amount of dissociation, very little HA, that means that this number on the bottom is approaching 0. The amount of reactants in this process are almost approaching 0, which means this K is approaching infinity. So we don't really have a number. They're just incredibly large. Okay, now again, products of reactants, when it comes to an acid-base reaction, let's do HCl here. It would be products, the H plus, okay, plus the conjugate base, Cl negative, not plus, I'm sorry, multiplied by, well, let's do the reaction first. I guess I'm kind of doing both in my head. So HCl dissociates into a proton and a chloride ion. All right. And if I write the Lewis, now this is aqueous, AQ, and this is aqueous, and this is aqueous. So we know that the KEQ, or Ka, is equal to the proton times the chlorine atom. Oops. Okay, I ran out of space there. So the chlorine atom. So we got the H plus times the chloride ion when we put it in an equilibrium expression over HCl. They're all aqueous, so we include them, and that equals Ka. Okay, and this has to go away. Okay, and of course, if I have a lot more what? A lot more products, free ions, than undissociated reactants, my K is a huge. So in any case, what we can do is we can evaluate, okay, the strength of an acid based on the equilibrium expression. Okay, so these equilibrium values tell a story about how well they dissociate. So as the Kas get smaller, okay, and the one thing you will notice that strong acids have very big approaching affinity-like numbers, and then all of a sudden it drops off very small. So there's no in between. And as I mentioned, the reason is that we have no ability for these conjugate bases to accept protons and act as a Bronston-Lowry base and return the reaction backwards. These reactions are really completion reactions that go forward because of the inability of these conjugate bases to reform the acid. So the reason why these guys are strong acids is because the size of these ions are so big, their charge density, okay, iodine, as you go down the periodic table from fluorine to bromine, so chlorine to bromine to iodine, the atom gets bigger because of the filled amount of electron energy levels. And then when they gain electrons, become negative, they get even bigger because of the shielding effects of electrons. So these things are becoming very big and -1 charged. So therefore, they have a tough time holding on to a proton. Therefore, the H plus is dissociated. And in part, that's some of the same reasoning applies here. These conjugate bases are terrible at reforming the acid. The rest of these reactions are weak acid reactions, and these really should be double arrow. These are equilibrium, weak acid, weak base. We have a weak acid, and we have a weak conjugate base. Okay, but there's a tie-in here. As the Kas get smaller, okay, as these numbers are showing, the strength of these acids decreases. Okay, notice something, hydrofluoric acid, which would be the fluorine I drew up here, is not a strong acid because of the size. Okay, charge density is really high. It's very small and -1, so the H plus is a tough time getting away. The bond energy is very high because of the great electronegativity as well. But the bottom line is, as these acids get weak, okay, as these acids get weaker and weaker, and their ability to break apart into ions, the conjugate bases are getting stronger in their ability to reform the acid, to accept a proton and be a Bronston-Lowry base. Okay? So the reasoning why these acids are getting weaker is the conjugate bases are getting stronger. So as the acid strength decreases, the base strength increases. And that's a pattern that's very important because we're going to learn tomorrow or in the next lecture that the Ka is inversely related to something called the Kb. So the Ka of the acid, if it's small, it's Kb, which represents the base dissociation constant, which represents how well these conjugate bases accept protons and reform the acid, must be higher. And we're going to learn what that equals tomorrow. So the ability of the acid drops to dissociate. That means that the ability of the conjugate base to reform the acid and act as a base by accepting a proton increases. And of course, that's also opposite. As the Kb of the conjugate base increases, okay, then the Ka, of course, as a Kb, I'm sorry, decreases, becomes weaker as you go up this group. The Ka, of course, increases. Okay, again, the Ka and the Kb are for the same chemical. Case in point, if we have H2S, hydrogen sulfide, or hydrosulfuric acid, okay, here's the acid and here's the conjugate base. If I have the Ka of 9.5 times 10 negative 8 for hydrosulfuric acid, its Ka is related to it, but has to be um, related in the fact that it must be lower. Okay, so if Ka is high, this is lower. So these change accordingly, and we're talking about the conjugate acid-base pairs here, as we talked about. So that's essentially what this table is showing. And if you look at some other things here, water's Ka is a very special number that we dealt with. That's the Kw that we talked about in pH. And look at OH minus. It's such a bad acid. Look at the value. Of course it's a base. And likewise for the ammonia. Okay. Now, something else I talked about today, the reason why neutralization occurs when you add protons and hydroxides, what's the equilibrium position between protons and hydroxides? Well, you guessed it, if the Ka for water, or we call it the Kw for water, is tiny, well, that must mean that, well, products over reactants again. There's a heck of a lot more reactants in the equilibrium position. Yeah, the reactants are favored. So if you put in too many protons and hydroxides, for those that have taken this, the Q, which is larger than the K, and the reaction proceeds spontaneously toward the water. More Le Chatelier's principle, but the bottom line is, in equilibrium position, we favor the reactants, so these guys are going to attack each other, annihilate each other to make water, and that's neutralization. Okay, so what we have now is the questions, and I had them on the other page. Let's look through some of them. Which of the following acids ionizes to the greatest extent? Well, what am I talking about here? Ionizing to the greatest extent, I'm looking for the strongest acid, highest Ka. So you look at table L and you find the strongest acid. Now I can look at this and say, well, weak acid, because it's not a top 5, weak acid, and now I have 2 top 5 acids. So I have nitric acid and sulfuric acid, and I know nitric acid, if I don't recall, okay, is higher than sulfuric, so nitric acid, okay, is the stronger of the acids based on that table. Okay, which of the following is amphiprotic amphoteric? Fancy name for, can act as a Bronson-Lowry base or acid. And as we looked about, HS. How do I know? Well, if I go to my table, I will see that HS is on one side, which means it can act as a Bronson-Lowry base that has some effect. Okay, it's a pretty strong Bronson-Lowry base as we go down the table. And we have HS somewhere else in this table. Oh yeah, here we go. On this side, acting as a conjugate acid. That's all I'm looking for. And I'm going to have to go back up for the questions. I'll figure this out soon. Now, what is the equilibrium constant for acetic acid? Mr. Grodsky, how do I know the name? Now, we haven't done naming yet, but we will. But a very simple way to do naming is this. If you have a polyatomic ion from table E that ends in 8, the acid's going to end in ic. So if you notice, I call this nitric acid because it has the what? Has the nitrate ion. So this is called the nitrate ion, and 8 becomes ic. So this becomes nitric acid. So if I'm looking for acetic, IC, okay, then I must be dealing with the acetate ion. And if you went to table E, you would see the acetate ion written as this, CH3, COO negative. Now, if it's an acid, it has the H, right? So you go to table right here, and we look for CH3COH, which, by the way, is vinegar, and it's 1.8 times 10 to the negative 5. 1.8 times 10 to the negative 5. Okay. Now you may say, Mr. Grazzi, you said hydrosulfuric acid before for H2S. Now, if things are binary and don't have a polyatomic ion, we use hydro, and then we add the ic. So hydrosulfur, sulfur, sulfur, ic, hydrosulfuric, HCl, hydrochloric, HF, hydrofluoric. And by the way, if you have the ite ion, it becomes OUS. So if I can find an ite ion here, I'm trying to find an acid, which I don't see here. So if I go to table L here, back, let's go find one. Let's do, no. Oh, here we go. This is HNO2. NO2 negative from the table is the nitrite ion. And nitrite, ites, okay, become OUS. So this is nitrous acid. So ites become OUS, ates become ic, and if they're binary, it's hydroic. So a little review here: hydroiodic, hydrobromic, hydrochloric. Oh, it's a nitrate, so nitric acid. This is the sulfate ion, so sulfuric acid. And let's go look at H3PO4. It's the phosphate, so phosphoric. So that's how we name. Okay, no big deal. And I'm almost done. Okay, which of the following equilibrium constants will have the lowest concentration of hydronium ions? Well, if you have the lowest concentration of hydronium ions, heck, you're a weak acid. So who's got the weakest Ka? Okay, who's got the lowest Ka? I would say this one, smallest number. Okay, which of the following acids has the weakest conjugate base? Wait a minute. If you've got a weak conjugate base, what kind of acid do you have? Ah, high acids, an inverse relationship. So which of the following acids is the strongest? Okay, weak acid, strong acid, strong acid. This one's higher on table L. Okay, and I'll just do one more. What is the conjugate base of HSO4 negative? Conjugate base, that means this is acting as an acid and will become a base once it accepts a proton. Oh, I'm sorry, once it gives off its H. Okay, so this becomes SO4 negative 2. So the conjugate base is what's left over after this donates an acid, and that's why that's the acid. You actually can look that up on the table as well. So continue on with this. If this helped, good for you, and I'll talk to you later.